So now we want to look at one example of using the Poincare-Bendixson theorem. So we're going to look at dx dt is mu x plus 2y minus x cubed, and dy dt is minus y minus 2x minus x squared times y. And we're going to look at the case where 1 is less than mu and 2 is greater than mu. So first of all, these equations obviously have an equilibrium at x equals y equals 2. And we're going to take it for granted that this is the only equilibrium, although we can show it using a computer algebra system. So next we're going to examine the stability of that equilibrium using local analysis. So we're going to calculate, going to take f to be mu x plus 2y minus x cubed, g to be minus y minus 2x minus x squared times y, and we're going to calculate the Jacobian. So j is df dx, df dy, dg dx, and gg dy. So that's going to be mu minus 2x squared, 2 minus 2 minus 2xy, and minus 1 minus x squared. We're investigating the stability of the equilibrium at 0, 0. So we'll look at J0, where we set x equals y equals 0. So that's mu 2 minus 2 minus 1. We want to know about the eigenvalues of J0. So we're solving the determinant, mu minus lambda, 2 minus 2 minus 1 minus lambda equals 0. So that's mu minus lambda times minus 1 minus lambda minus 2 times minus 2. And all that's equal to 0. So we can multiply this out. We've got minus mu plus lambda minus mu lambda plus lambda squared plus 4 equals 0. So that's lambda squared plus 1 minus mu lambda plus 4 minus mu. And we can hit this with a quadratic formula to find lambda, that's minus b, minus 1 minus mu, plus or minus square root of b squared, 1 minus mu squared, minus 4ac, that's minus 4 times 4 minus mu. All over 2a, that's just a half. So lambda is mu minus 1 over 2 plus or minus a half, and then we'll multiply out the square root. So that's 1 minus 2 mu plus mu squared minus 16 plus 4 mu. lambda is mu minus 1 over 2 plus or minus a half square root of mu squared plus 2 mu minus 15. And finally we can rewrite this as lambda is mu minus 1, 2 plus or minus half square root of mu plus 1 squared minus four squared. And remember, we've got 1 less than mu less than 2, which means that mu plus 1 squared is going to be less than 4 squared, which means our square root is going to be negative. And so the stability of the system is going to depend on the real part. So the real part of lambda is going to be mu minus 1 over 2. And because mu is always greater than 1, so it's going to be greater than 1, and so the system will be unstable. According to our local analysis. So the equilibrium at 0, 0 repels orbits. So that means by Poincaré-Bendixson, if I can show there's a trapping region, so if I can show the region where trajectories move in and are trapped, then because I can exclude the equilibrium at 0, 0 from this region, the system will be stable. And I'll look at that in the next video.